All right, guys. So in the previous section, we took a look at an extremely common and very useful amplifier circuit called the inverting amplifier circuit. We want to continue our study of circuits that contain operational amplifiers. There are a total of 3 more that we're going to take a look at. And right now, we're going to take a look at another one that shows up absolutely everywhere in electrical engineering, one called the summing amplifier circuit. We'll see at the end why its name is so chosen. And we are going to make similar assumptions to the assumptions that we had made previously for the sake of simplicity analysis. So without further ado, let's actually hop into the analysis itself. And right now we want to talk about the summing amplifier circuit. Now, previously, we stated a goal, and I want to state a similar goal, one that's not exactly the same, and you'll see the reason for it here in a second. But it can be written down as the following. We want to be able to find, through our analysis, the voltage output as a function of the voltage inputs, as well as the rest of the components that are in the amplifier circuit itself. Now, notice I very deliberately chose voltage inputs, unlike in the previous amplifier circuit where there was one single voltage input. One of the things that characterizes the summing amplifier circuit is there are 2 or more voltage inputs, right? Depending on how many branches you actually have within your summing amplifier circuit. So let's go ahead and write down what the circuit looks like. Let's draw the circuit schematic. And we begin with our operational amplifier. Here we have our non-inverting input and our inverting input. We then are going to connect it to our external voltage supplies, plus VCC and minus VCC. On this end, we will have our voltage output with our node voltage V0. And here, at the non-inverting input, we're going to go ahead and ground that. At the inverting input, it's going to be a little bit more interesting. We do have, as always, our feedback resistor. Remember that feedback resistor there is there to make sure that we can work within the linear region and that our op amp doesn't saturate either in the positive saturation region or the negative one. So here we have RF. And here we actually have a portion that splits into 3 branches. Along the bottom branch, we have one small resistor that we're going to call RA. We're going to have a second resistor over here that we're going to call RB. And then at the very top branch, we're going to have one last resistor that we're going to call RC. And each one of these resistors, RA, RB, RC, are actually going to get hooked up to 3 separate voltage sources. So here at RA, we have one voltage source with this polarity that we're going to call VA, hooked up to resistor VB. We're going to have a second voltage source that we're going to call VB. And then lastly, at the very top, hooked up to RC, we're going to have one last resistor that we're going to call VC. Now, before we go through the analysis, let's actually state very clearly what our assumptions are. So we're actually going to assume that this is an ideal op amp, which, if you'll recall, means 2 things. The first is there's an input voltage constraint, and that is that the node voltage VP and VN, it might not be 0, but they do have to be equal. The second one is the input current constraint, and that tells us that for an ideal op amp, the currents flowing into the inverting and non-inverting inputs are 0. I'm going to call these 1 and 2, and you'll see where these get used in a little while. Now that we have that assumption clearly stated, let's go back and set the scene in order to do the analysis. Since we will be using the node voltage method in order to analyze the circuit, we really want to clearly identify and label the nodes. There are various nodes here. One node that we actually have is this one. And notice I'm circling the whole thing here, just so that you can see very clearly where these currents are actually going to be kind of coming from. We have another node here. We have our output node over here. And it's not as easy to see, but there are three last nodes. There's one node there, there's another node there, and then there's one last node right there. Now that we have the nodes clearly identified, let's go ahead and start defining a few variables. Here at this node, we have the node voltage Vp, and in general, we have a current I sub P that's going to be flowing in from that node into the op amp. So this is our node P. Up here, we have our node N. Our node voltage there is Vn, and in general, going into the op amp, we have a current I sub N. Over here, we have our node voltage V naught. Here, this is the node voltage VA, VB, and VC, and now we have labels and variable names associated with each node. Now, another thing that this op-amp circuit is going to share in common with the one that we analyzed previously, as I mentioned before, from my point of view, and there are multiple ways in which you can analyze the circuit, but I've always found the node voltage method the most convenient. So that's the one that we're going to stick with. So we're actually going to use the node voltage method. Analyze the circuit. And remember, it means that with our convention, there are no currents flowing into any nodes. They're all flowing out. And according to KCL, the sum of the currents flowing out of any node has to add up to 0. Now, let's go ahead and focus in on one node. So I'm going to use KCL at node N. And again, the version is that the sum of the currents flowing out of this node have to add up to 0. So let's take a look at node N, and let's see what we potentially could have flowing out of there. Now, notice that we could have a current flowing from this node through this resistor that way. Starting at node N, we could have another current flowing that way, another current flowing that way. We could also have a current flowing from node N all the way out to the output, and a current flowing from there to there. So notice that because of the branching that we have here, there are a total of 5 currents that are flowing out of node N. That means that when we write down KCL, we're actually going to have a sum of 5 separate terms. And let's go ahead and write down what those are. So let's start with the one at the bottom. So here we have V sub n minus V sub a divided by RA. We also have V sub n minus V sub b divided by RB. We also have for the last branch V sub n minus V sub c divided by RC like this. So that takes care. Let me erase these in the order in which I wrote them down. So we had the current there, the current there, the current there. We have the sum of our 3 terms. Let's take care of the current there. Let me put back my feedback resistor. And that current is going to be Vn minus the output voltage V naught that's flowing through the feedback resistor. That's Rf. And then lastly, we do have the current there. That's I sub n flowing out of node N. So we have now plus I sub n, and that's equal to 0. Call this equation 3. Now, just like previously, we had made a quick observation. And that observation was quite helpful in the sense that it allowed us to determine what V sub n was. The observation was that this node P is hooked up directly to ground. That tells us exactly that V sub P is 0. Right? So here, the important observation is that V sub P is 0 because it's to the ground. Now, because V sub p is 0, we can actually use this fact in equation number 1, right there, and conclude that V sub n is 0 as well. So here, by equation 1, and V sub p being equal to 0, we conclude that V sub n is equal to 0. We'll call this equation 4. And notice that we can actually use equation 4 and equation number 2, that I sub n is equal to 0. This one and this one. We can use those both in equation number 3 to simplify that equation quite a bit. Right? So let me write this down. So using 2 and 4 and 3, where we had V sub n minus V sub a over RA plus V sub n minus V sub b over RB plus V sub n minus V sub c over RC plus V sub naught, the output voltage. V sub n divided by, let's see, V sub n minus V sub naught over RF, the feedback resistor, plus I sub n is equal to 0. Well, a lot of these things disappear. So that disappears, that disappears, that disappears, that disappears, and even this disappears. That simplifies our equation immensely, right? So here, this equation can be rewritten as minus VA over RA minus VB over RB minus VC over RC. And I'm going to do something right off the bat so I don't have to rewrite this equation. This term right here, along with its minus sign, I'm going to add that to the opposite side. So here, I can move that to the opposite side. I get V naught over RF positive, like this. Now, if I multiply everything through by RF, right, one way in which I can rewrite this, and on top of that, I'm going to also go ahead and factor out all of these minus signs. I can rewrite the entire equation as V naught is equal to minus RF over RA times VA plus RF over RB times VB plus RF over RC times VC, like this. This is as far as we can go with our circuit. So we did actually achieve our original goal, which was to find V naught as a function of the voltage inputs. These happen to be VA, VB, and VC. Now, I do want to make one last observation. And this is, let's say RA is equal to RB is equal to RC. And I just define this as a new variable R sub S, right? Then the above equation becomes V naught is equal to minus. And notice that since RA, RB, and RC are all equal, and they all have RF in the numerator here, I can factor that entire thing out. We have RF over RS, VA plus VB plus VC, and what I really want to concentrate on is this part. Notice essentially here, you have the sum of 3 voltage inputs. This is where this amplifier circuit actually ends up with its name. This is one of the reasons why they call it the summing amplifier circuit. On top of that, one last thing to note is that there is a minus sign there. So not only is it summing all of the voltages, but it is also inverting the voltage, just like the inverting amplifier circuit. And we'll see a few examples in a little while to see how we can use this circuit in order to do things that are useful.